Welcome back to another lecture of time series analysis. This is lecture number 3, and now we get to actually do some real statistics. So let's go see what that's all about. In this lecture, we'll be looking at autocovariance and autocorrelation, how to estimate it and what it can tell us about time series data. And at the end of this lecture, we're going to get to look at RStudio and analyze a data of prescription drug prices in the US from the 80s to the 90s, I believe. So let's go take a look at that. Welcome back to another lecture of Stat 479 Time Series Analysis. Today we'll be finishing up Chapter 1 in my lecture notes. Last time we ended with the idea of estimating the mean of a stationary process. So let's revisit that and remember what we were talking about in the last video lecture. So, right, the main thing we were looking at was the idea of a stationary process. And this is going to be really important because a stationary process in the weak sense, which is kind of the only one we need for this course, says that the mean, that is the expected value of xt, is not a function of time. And furthermore, the idea that the autocovariance function kx at time points s and t is going to equal to, well, the same thing shifted by any amount r. This is for, I guess, s and t and r, I guess whatever they're, I guess integers or numbers. We'll just say numbers. Doesn't really matter. The main point is that the mean is invariant to shifts in time, which basically says that it's constant throughout all time. And furthermore, we have that the autocovariance function is invariant to shifts. So it still depends on how far apart the two time points are, but it doesn't matter where they fall in the process, the time series process. It could be at the beginning, they could be at the end. As long as the two time points are the same distance apart, they'll have the same autocovariance. And this gives us the idea of a weakly stationary process. And this is going to be really important because, well, again, if we want to estimate the mean or the autocovariance, we want to make sure it's the same at every time point. Otherwise, we can't estimate it, because if the mean starts off at, say, 0 here and it's 22 there, then it's hard to estimate it because we can't use these points to estimate the mean at these other points. If the mean's the same in all time, then we can use all the data points to estimate the mean. And that's exactly what we ended the last video lecture discussing. So in the last video lecture, we ended with the idea that if I want to estimate the sample mean, or estimate, I should say, calculate the sample mean to estimate the, I guess, population or global mean of the process, the time series process, the mean, then what I'm going to do is just use x bar, which in this case will be the sum. I think I was using little t, that's right, little t from 1 to capital T of xi. So if a process is stationary, then our estimator for the for the mean of the process is just the usual sample mean denoted x bar. And what we did last time was show that the variance is a bit different now than it normally would be. The variance is in some sense inflated a bit based on the fact that this data is dependent, or the time series data points are dependent on each other. So let's go a step further, because the mean is great and okay, that's interesting, but what we're really going to be interested in is estimating the autocovariance function, and specifically the autocorrelation, because this is going to give us a key tool for exploratory analysis in time series data. All right, so now what we're going to talk about is estimating the autocovariance. The autocovariance Kx. Okay, so how do we do that? Well, we do that kind of just how you think we would do that, which is first to recall that for xt stationary, we can write the autocovariance function as having a single argument. So instead of having s and t, we can just choose some value h, which will be the offset. If h is 0, the 2 points are on top of each other. If h is 1, 2, 3, 4, and so on, they start to get further apart. So in this case, we can just consider basically a single argument for the autocovariance function, and then for, I guess, any h in, well, okay, so any h from, let's say, 0, 1, all the way up to t minus 1, because if we have capital T total data points, the biggest lag we can have is t minus 1, because it would be the last point minus the first point. We're not going to go that far out anyway, but we'll talk about in a second. But hypothetically, yeah, we could have an autocovariance calculated for any lag from 0 all the way up to t minus 1. And I'll just point out here, h is a lag. So I'll throw out the term lag a lot. We'll look at that more when we plot the autocovariance, or the estimated autocovariance function, correlation function, that is. But just to make sure that you get the terminology that I'll keep saying. Right, so then the question is, well, what's the estimator? Well, the estimator in this case is going to be k hat at some chosen lag h, and it's just going to be the average 1 over t times the sum t little t from 1 to capital T minus h. So that's going to be kind of an important thing to take note of, and we'll talk about that in a second. And the summand is going to be t plus h minus x bar and xt minus x bar. So it's going to look a lot like the sample variance or the sample covariance between two random variables. It's just that here we have the same x's on each side, just offset by a lag or an offset of h units. All right, so there's a couple things to note here. Well, first of all, the number of terms in the sum is dependent on h. So that's one thing to note. We'll say note that there are t minus h terms in the summation. So what does that mean? Well, that means that as h gets bigger, the number of terms we have to estimate the autocovariance decreases, it shrinks. And that means our estimate will actually not be as good as h gets large. Now, for time series data, typically, we're assuming that capital T is fairly big, something that you've been watching a process for a while. It could be 100, it could be 1,000, or so on. I mean, if you have daily, let's say, temperatures or daily stock prices or daily COVID infection rates or things of that nature, then you can imagine that even in a year of watching a process or a couple months, you'd have at least 100 observations or more. In contrast, when we're trying to estimate the autocovariance, typically we're only interested in the first so many values of h. I forget if there's a default in R, but I suspect that after about 10, h is equal to 10 or 15, you're probably not going to care too much anymore. So this issue is not, it's not super critical in the sense that it's going to cause major issues, but it is something to remember that if you want to estimate an auto correlation or covariance out at lag 50 or lag 70, it probably isn't going to be as good of an estimate as it would be at lag 1 or 2. And the lags 1 and 2 would be the most relevant ones for statistical purposes. Right, so that's the little disclaimer about how this summation works. Also, we have the notion of a autocorrelation function. So we also can estimate, well, we talked about the autocorrelation function in a previous lecture, but in this lecture, we are going to estimate it. Missed an N. There it is, function. Cool. All right. So the estimated autocorrelation function, which I'm going to write as rho hat with an argument of h at a lag of h, is just going to be the estimated autocovariance function. It's really easy to switch covariance and correlation, so I have to make sure I don't mess that up. And the divided by the autocovariance at 0. So this guy down here, let's do blue. This guy down here is just the variance, or an estimate, I should say, of the variance. Remember, it's stationary, so the variance doesn't change. So the autocovariance evaluated at 0 is just an estimate of the variance of this process. So really, we're doing exactly what you would think to do if you wanted to get a correlation, which is take the covariance, divide by the variance, and now we have a correlation. So that's going to be important because we're going to be using this a lot to understand what our time series data is, I guess, telling us, or what we can learn about our time series data through the estimated autocorrelation function. And that'll come later in this lecture. But before we're done with that, there's a couple more things to point out. We can also estimate the cross-correlation function. The cross-correlation function. And the cross-correlation function is going to be estimated, well, very similarly to what we saw above. In this case, if we have an x and a y, and at lag h, then we're just going to say 1 over t, that's the sum t from 1 to t minus h again, and then we have an x t plus h minus x bar, and now a yt minus y bar. And here we're assuming that both x and y are stationary processes and that they're jointly stationary as well. Otherwise, it doesn't really make sense to do this. And lastly, before we end our ever-increasing list of so I must have made a mistake already, right? It's not the cross-correlation function, it's the cross-covariance function. Whereas the cross-correlation function, which I want to write down as the secondary thing, is exactly, again, what you would expect, which is it's just the cross-covariance divided by an estimate of the variance. So in this case, if we have rho hat x, y, h, then what we're going to do is we're going to take our estimate k hat with the x and the y to indicate that it's a cross-covariance function at lag h, and we're going to divide by the square root of, well, in this case, just the variance of x and the variance of y, which is denoted in this way as kx at 0 and ky at 0, with the hats indicating that what we're doing is we're estimating the variances. So again, the formula a little messy, but it's not too bad, and it's kind of what you'd imagine we would want to do. Okay, so now what we can do, of course I don't actually have the PDF ready to go, so we're going to take a quick pause. All right, and we're back from our quick pause. And where were we? Well, what we were doing is we wanted to, again, look at some examples of estimated autocorrelation functions in R. So that's what we're going to do right here. Excellent. So let's dig into this a little bit. Maybe I can expand this slightly so we have a little bit more room to look at it. Good. So if we use the function in R, so this is the, I'll say from the R function ACF. I think that's just in the standard stats package, but I'll have to double check that to make sure I'm not misremembering that. So what it does, and it looks like here the default lag or maximum lag is 15, is that it computes the autocorrelation function, or I should say it estimates the autocorrelation function from some data that you give it at various lags, starting at 0 and going by default up to 15. But of course, you can always change that as a parameter in the function call. Now, first of all, at 0, the autocorrelation is always going to be 1 because you're taking an estimate of the variance and dividing by the same estimate of the variance. So the autocorrelation, so I'll say ACF at 0 is always 1. So that's the first thing to note. But now let's look at these pictures we have here a little bit more closely. So first of all, we have white noise in the top left corner. Now, the first thing we notice is, okay, we have that big spike at 0, which has to be there. But then every other little line there is pretty small. And what that's telling us is what we would expect. And what we expect is that white noise, right, is uncorrelated. At the very minimum, it's uncorrelated noise. And that means the auto covariance will be 0 at every lag that's not 0. So at every positive lag, we're going to have an autocovariance at 0. In this case, we're estimating it from the data, so it's not exactly 0, but it's going to be close. So here, the autocovariance at lag h is going to be 0 for h greater than or equal to 1. In practice, right, k hat at h is going to be approximately 0. It's not exactly 0, of course, because we have a finite amount of data, but that's what all of these points in here are telling us. What they're telling us is that there's no significant autocorrelation at any positive lag. Remember, the autocorrelation is a symmetric function, so we only have to consider positive h. If we looked at negative h, we'd get the exact same plotted answers, but in the sort of a mirror image, right? Because it's a symmetric function about 0, right? So that's the first thing, and that's one really neat tool or usage for the estimated autocorrelation is that we can use it to kind of visually say, this process looks like white noise because I don't see any detectable correlations at any positive lags. Now, in contrast, if we try to apply this to the random walk, so in the random walk case, this is the process xt is equal to xt minus 1 plus wt. And if you recall from, I think, the first lecture, this is not stationary. So again, right, computer programs, R or any other stats package you're using, isn't going to stop you from computing an auto covariance or autocorrelation for a non-stationary process. but the results don't make sense. And in this case, we see these giant spikes at all positive lags. So even going out to a lag of, say, 15, we still see a very strong positive autocorrelation. And if you see that, it's kind of indicated that, there's probably some non-stationarity here, and we should probably investigate that further. Now, we will be looking at actual tests, statistical hypothesis tests for non-stationarity as we go further in this course. But for now, we're just kind of exploring the data visually and graphically, and we can use the ACF to do that and identify that, okay, if I see an ACF that looks like that one there in the top right, there's probably a problem with stationarity. It looks a lot like a random walk. Now, going forward, if we have the moving average process in the bottom left. So the moving average, this is the moving average at order 9. So in this case, I took white noise and I took a window of length 9 of width 9, and averaged all the points and slid that window across the white noise process to create a moving average process like we talked about in the first lecture. In this case, we see some pretty interesting behavior. What we see is a very steady linear decrease in the auto correlation function. So it looks like this basically until it hits 0. And notice that it hits 0 right around 10, I guess maybe around 9 to be exact. That's going to be important because what we're going to find out later in this course is we can actually use the ACF function to estimate the order of a moving average process. And we're going to see behavior like this, where we see steady decrease in the autocorrelation until it becomes 0. So again, at this point in the course, we're just looking at these pictures and trying to gain some intuition. We'll make this more precise in later lectures. And lastly, if we look at the bottom right, we see an AR2 process. I think in this case, I used a non-stationary AR2. Actually, I have to double check that because it might actually be stationary. We'd need to compute the auto. We'd need to compute the auto covariance or auto correlation function to determine the stationarity of it. In this case, okay, we still see a decrease, but if you look closely at this plot in the bottom right, it doesn't look as linear. It's not a straight line decrease to 0. It looks almost like some type of an exponentially curved decrease to 0. Something like that with a terrible drawn arrowhead there. So the AR process is going to have a different type of behavior when we look at its ACF function. In this case, it's going to decrease in kind of a geometric fashion. It's going to decrease like, let's say by a half, and then a quarter, and then a fourth, and an eighth, and a 16th, and so on, whereas the moving average is going to decrease linearly. Now, it's not always straightforward when you're looking at real data what type of process you have by just computing the autocorrelation or estimating the autocorrelation function, especially if you have moving average and autoregressive pieces within the same process. But again, this will at least give us some idea of how to look at our data and how to understand a bit about what's going on, because so much of time series is about exploratory analysis. We're not just going to collect our data and run a hypothesis test. We're going to be staring at it for a while and trying to figure out, okay, what's going on? What type of models are here? Is it stationary? Is there a moving average piece? Is there an autoregressive piece? Et cetera, et cetera. All right, so that more or less, I think, finishes up what I wanted to talk about autocorrelation. One other side note, though, I wanted to mention before we move on to the testing for white noise is note that in the definition of k hat, we divide by t. And when you first look at this, you might think to yourself, well, why are we dividing by t and instead of dividing by, say, t minus h? Or because the total number of terms in our sum is t minus h, but we're still dividing by capital T. The reason is that we want our estimator to be positive definite. This is so that k hat will be positive definite. And this is going to be a very important property. Whenever we're dealing with covariances, we want positive definiteness because that's how covariances are defined. So if we're estimating a covariance, an AutoCovariance, we're going to want that thing to be positive definite. And I won't get into all of the details. I believe in the textbook there's a derivation of why this is true, but mostly the idea is just to intuitively understand that we want this property to hold for our estimator, and that's why we write our estimator in the form that we chose. All right, so we're going to move on to the next part of this lecture, which is, can we detect white noise? Because when we have a noisy process, the first thing we might want to know is, well, is it a white noise process, or is there more structure here that we want to understand? And if you recall from the first lecture, we kind of looked at different examples of time series processes, and we had white noise next to, say, an autoregressive or a moving average process, and it's not always clear that one process has more structure to it and the other is actually just completely uncorrelated white noise. So we can use this idea of the estimating the autocorrelation function or the AutoCovariance function to detect white noise. So let's talk about that. This is sliding off the page. This is detecting white noise. Section 1.33 in my typed up lecture notes. Right, so what we saw from, I'll say from above, we know that K, that is the AutoCovariance, actually I should replace the X with a W. So the AutoCovariance for white noise, even weak white noise, but certainly for strong and Gaussian white noise as well, is going to take on two values. It's going to take on 1 if H is equal to 0. And it's going to be 0 for all other H. Again, we only really need to consider positive values of H, but it's a symmetric function. We can also consider negative values if we really want to. It's going to be the same thing. Basically, so we need to determine if, okay, another slight error I made. This is not the AutoCovariance. Again, this is the autocorrelation. So I'm being slightly imprecise. This is supposed to be a row of W. We could look at the AutoCovariance, but then the 1 would be replaced by a sigma or a sigma squared. So of course the same idea makes sense, but to be precise with the way I wrote this down, we should be writing autocorrelation. Like I said, it's really easy to flip these two around, so I'll try to be as precise as possible. Anyway, yeah, we need to determine if the estimated, I'll say K hat W at H and rho beta and rho, the estimated rho hat, the estimated autocovariance at H is small enough to be imprecise in the language for H not equal to 0. Because as I mentioned in the picture above, we're not going to have exactly 0 for our estimated autocovariance or autocorrelation. Instead, what we're going to have is some small value, and we need to know statistically, is that value small enough to claim that it's close to 0? And that's exactly what we're going to look at here. So how do we get to that? Where are we here? Yes. So the first thing we take note of, so the first note is that basically, since WT is mean 0, we can write the estimated autocovariance of WH to basically be what we had above, but I'm going to throw away the sample mean. This is just to make things slightly easier to look at mathematically. We can justify this if we really took some time to write it all out, but it's not really worth it in this case. We're just going to say, I'll just put it off to the side. This is because W bar is really close to 0. So we'd expect the estimated auto covariance function to be something that looks like this. And the reason why we do this is so that we can compute the variance of the estimated auto covariance. So we're kind of computing a variance. We're going to compute the variance of our estimate for the auto covariance, and we're going to show that that will go to 0 and how fast it goes to 0 in the case of white noise. And that's going to tell us how small we expect the estimated auto covariance to be when the actual answer, the actual auto covariance is 0. Okay, so I hope you're kind of hanging on there. There's a lot of terminology and excessive use of the word auto covariance. But yeah, let's push ahead. So what do we have here? Yeah, so first is for H not equal to 0, we have that the expected value of WSWT, I guess where I should write this out better. WT plus HWT is equal to 0. All right, because they're independent or they're uncorrelated. At the bare minimum, they're uncorrelated and have mean 0. So the point is that this thing is also going to be mean 0. Furthermore, we have that the variance of our K hat for white noise, well, what's that going to be? That's going to look something like, well, 1 over t squared, because I can take the t out of the equation. And then I have to compute the variance of the sum. I have to be careful not to immediately switch the order because of correlations, or I guess potential indices that are the same. So here we have t minus h of w t plus h wt. All right, so now when I apply the variance to this entire thing, I end up with a double summation because I'm kind of, remember, when I'm taking a variance, I'm kind of squaring the thing inside the variance, and we're throwing away the mean term to try to save the mathematical headache. But if you really wanted to, you could throw a whole bunch of W bars in there, and it's just going to make everything quite messy, but you can still fight your way through it. Anyway, where were we? Yes. So what we're going to do is we're going to now sum t from 1 to capital T minus h. We're going to sum s from 1 to capital T minus h. And we're going to look at the expected value of w s plus h, ws, wt plus h, wt. Okay, now what's neat about this is that it's always going to be 0 except in very few cases. It's only going to be not 0 when s is equal to t, because, well, I'll write it out. So this is actually going to just be t from 1 to t plus h, or not t plus h, t minus h, capital T minus h to be precise, of the expected value of wt plus h squared, wt squared. And the point that I also wanted to make here is that all other terms are equal to 0. This is because if the indices don't match between s and t, then what happens is we end up with the expectation of a wt or a ws, and that's going to be 0. So that's just going to destroy that entire term in the summation, in the double sum. And the only time that we're not going to get 0 is when s and t are equal to each other, because then the only things inside the expectation are w squared, and w squared, the expectation of w squared, is not 0. It's actually going to be sigma squared, in this case, sigma to the 4th, because what we do is we take this, and because the white noise process, is uncorrelated, we can split this into 2 pieces as such, and then we can show that this is in fact sigma to the 4th. It's sigma squared times sigma squared, which means that our final answer ends up being something that looks like t minus h divided by t squared times sigma to the 4th, which happens to be less than or equal to just sigma to the 4th over t. I guess strictly less than for h not equal to 0. So if I want to be a little bit more precise, I'll get rid of that. If I can get rid of that. Oh, I guess we're not erasing. There we are. So this value here is key. So what it tells us is that for our AutoCovariance function, when the lag for the white noise process, when the lag is not 0, the AutoCovariance estimator will have mean 0, so it should be plus or minus somewhere around 0, and it has a variance that looks like sigma to the 4th divided by capital T. So as the data size t, the amount of points in our time series increases. What that means is that the variance of our estimator will decrease, and we'll expect the value of k hat to be closer and closer to 0. So how close should we get to 0? Well, if we go back to the autocorrelation function, we find out that therefore, for rho hat of w at h, we have mean 0 and variance 1 over t, because what we effectively do here is we just divide, I guess, by the variance term, which in this case would be the variance of the variance. It would be sigma to the fourth. It's a little bit of a pain, but that's roughly what happens here. And as a result, so we can look at, I'll say, plus or minus 2 standard deviations from the mean from 0. The mean. And this, I'll say, is being what? It's going to be plus or minus 2 divided by the square root of t. And if we go back up to those plots further up the page, we're going to see, if you were looking closely, we see these blue lines, these blue dotted lines above and below 0. And these blue dotted lines are going to be the plus or minus 2 over the square root of t. For whatever t was, I honestly don't recall off the top of my head how I generated this data. But that's where these blue lines are going to be. And it's just going to be a rough guide. Again, this isn't a proper statistical hypothesis test. It's just a rough guide. And it says that, okay, if the autocorrelation is supposed to be 0, then the estimated autocorrelation will probably be within about 2 standard deviations of the point 0. And that's going to be these plus or minus blue dotted lines that you see in the ACF function when you plot it in R. So that's what we can use. If, for example, if we zoom in really far, maybe we find that there's one point that's ever so slightly above the threshold. That doesn't mean that it's not white noise. Again, this is not 100% precise. It just says that, okay, with probability, say 95%, we would expect that the estimate would lie within these 2 dotted blue lines. So it's, again, more of a qualitative rule than a proper statistical hypothesis test, but still something worth understanding here. Let's zoom that back out. All right, so that is really everything we were going to do in chapter 1 of my online lecture notes. So with that, I think we can start chapter 2. Okay, and we're back, and we're going to start chapter 2 of my online lecture notes now, which is looking at statistical models for time series. So now that we have a rough idea of the different pieces that make up a time series, things like white noise and autoregressive and moving average processes, and notions of the mean and the AutoCovariance and autocorrelation, we can now go a little bit further and talk about actually modeling time series data. So let's get into that. Right, so the first thing we want to do is, well, first I'll write down the title. Statistical models of time series. And the first thing we need to do is a couple definitions that are going to, well, maybe be a little annoying at first, but also help to save us some headaches in the future when we can use them for writing down our time series in a simpler manner. So the first thing we need to discuss is what's called the backshift operator. The backshift operator. And what this is going to be is it's going to be denoted as, well, B. B for backshift. And this is defined such that B applied to a time series or stochastic or discrete time stochastic process xt is just going to return xt minus 1. All right, so that's not the most exciting thing, but we can also iterate it. We can iterate it to the kth power, and if we apply that to a time series process, we just take it t and we subtract now k. So all we're basically doing is shifting our time series back in time by 1 or 2 or k units. Again, not the most exciting definition, but it will be convenient in the future. This also leads to the idea of the forward shift. The forward shift operator, which can be denoted as B inverse. And it just takes xt and does probably what you think it's going to do. It's going to add 1 to the index. And of course, we can iterate this, and we can also write things like B inverse, B is equal to B, B inverse is equal to I, where I would be the identity operator. Again, at first, when you see this, it might seem a little silly, but it's going to actually be very important later on. So similar to the backshift operator, we also have the difference operator. And the difference operator is, well, going to be defined as our upside down delta. I guess nabla, if I'm correct. I forget which one, or if that's the other one. Whatever it is, it's our difference operator. And this is defined such that if we apply this to xt, what we get is well, a first difference, which is going to be xt minus xt minus 1. So we basically take the process, and then we take the process shifted 1 unit back in time, and we subtract 1 from the other. So we're looking at the change. This is kind of similar to like a derivative for discrete time, right? We don't have continuous time in our setup here, and even if we did, we'd have to deal with the issue of a stochastic process, which wouldn't be differentiable in the usual sense. But forget about that for a second. The idea is that if we have something discretely that we're watching at fixed time intervals, if we want to look at a derivative of that process, we can take a first difference. And we can write this first difference in terms of the backshift operator. So this just happens to be 1 minus b times xt. So there, the backshift operator can actually be used to define the difference operator, or the first difference. The first difference, because what we can do is now we can iterate this to get the kth difference. And the easiest way to write this is to write this as 1 minus b applied k times to xt. And as a result, we're actually going to get a binomial sum, or a binomial series, I guess summation. Here we're going to take I from 1 to k, and we're going to get a minus 1 to the I, and we're going to get a binomial coefficient k choose I, and we'll have xt minus I. So the formula is quite a little bit messy, but what we can do is we can do a simple example just to show that this works. We can do this for the second difference. So if I want to apply the second difference, well, I know what happens when I apply it once, right? You can write this as the first difference of the first difference of xt, which is the first difference of the process xt minus xt minus 1. Because this operator is linear, I can pass it into the parentheses and get something that looks like this. And then I take the first difference of each of these piece one by one, to get something that looks like this. Let's say x t minus 2. And then when I put it all back together, what I get is the second difference, which is going to have our binomial coefficients 1, 2, and 1 with an alternating sign minus 2. So here we have our binomial coefficient, and we also have our alternating sign popping up there and there using red and green. So, right, we can do this, and again, the formula just becomes more and more complicated, but it allows us to write this in a much nicer form. Now, if you're reading along in my online lecture notes, I put in a fun definition. You can actually define a fractional differencing operator, where here k, instead of being an integer, a positive integer, would be some, I guess, real number, and our positive real number, which then it can be written in terms of a summation with gamma functions. So that's always good times, but we're not actually going to need that for this course. Just a fun fact to keep in mind. Whenever there's something in math, it always seems to be generalized to another level, right? That's sort of how mathematics goes. Okay, so now that we have our two kind of technical definitions, what we want to do is look at time series models versus linear regression models, because I think, again, as I've mentioned before, linear regression is a really good starting point to kind of branch off into a time series. So let's pretend for a second that we're in linear regression class. Linear regression. And what we might want to do is estimate our xt by some linear model. In this case, I think I was using, I'm using zt as my independent variable. I think I had t in 1 and beta p, say, if we have a p dimensional or p predictors or independent variables. Then we have something that looks like this. So this would be our linear regression model. We have our, we'll say p independent variables. And this would be IID, I guess, errors, or we'll just call it noise. Yeah. So we have this set up, and what do we know? Well, we know that if we were to write this as x is equal to, I guess, z beta in matrix form, z beta plus epsilon as matrix vector multiplication, then we know from linear regression class that the Gauss-Markov theorem says that the least squares estimator is best in the sense of it being a minimal variant, unbiased linear estimator, i.e. we have that beta hat is just going to be our Z transpose Z inverse Z transpose X. Okay, so we have that, but remember what the Gauss-Markov theorem wants. The Gauss-Markov theorem, right, assumes that epsilon t is IID. We need it to be, I guess, mean zero and all the other stuff, but effectively we want it to be completely independent. now, or at least uncorrelated. Sorry, I think, yeah, just uncorrelated. Let's just double check that, actually. I wonder if it is just I think it might just be uncorrelated. Regardless, the point is that in time series, we may not have that. So the idea is that that's great if we're in linear regression class, but if we're in time series class, as we are, time series, it's really easy to make a typo and write times series, and it's just one of those things to watch out for because it just looks bad in writing. And I've definitely made that mistake myself when you want to tack an S onto time, but it's time series. And in this case, we'd consider, in some sense, the exact same thing. We would have some deterministic piece, which we can write in terms of our Zs again and betas. This is just one model for a time series, by the way. But we would have something like this. But now what we're going to do is replace our epsilon with a yt. So in this case, what we have is, this is the deterministic piece. And we would have yt, which is some stationary process, which is not, I'll say, but not white noise, WN for white noise. Not necessarily white noise. It could be, and if it is, then we're back in the linear regression setting. But the point is that we could have the exact same setup as linear regression, but now our noise variable is some stationary process, and that's going to complicate matters as it usually does. So if, there we go. I'll say, therefore, if we were to compute beta hat as before, the residuals, well, okay, I guess the residuals would be something that's going to look like xt minus, let's just say x, I guess, minus z beta hat, just to make it a little bit nicer to write out. Let's just say this is R. Then RT is, I'll say, approximately going to be YT. It's going to be, again, the residuals are not going to be YT, but they're going to be something kind of close to it. But the problem we're going to find out here is that, I should say, and RT may not be, okay, so there's some subtlety here. I want to say it may not be independent or it may not be uncorrelated, but of course it's actually never, strictly speaking, uncorrelated. The subtlety comes from the fact that even if you have IID errors or white noise, then the residuals will actually live in a slightly lower dimensional space, so there will be some correlations there. But for a very large sample size and a very small number of parameters p, we would expect that the residuals would more or less look like some random noise. We wouldn't see any structure. So what we get here is that we can take the residual process and look at it as a time series. And that's the key difference between, I guess, taking data and applying a time series model versus, or thinking of it as a time series versus thinking of it as a linear regression, is that the errors could have this temporal correlation, and it's something that we want to understand. Now, I should say here, I'm not considering things like autoregressive or moving average process at the moment. I'm just looking at some deterministic piece plus some stationary piece, which could be autoregressive, it could be moving average. We haven't discussed exactly what YT is, other than it being a stationary process. But now that we have this framework in mind, and we still have about, say, 20, 30 minutes left to discuss, we're going to take a quick break, and I'm going to switch over to RStudio, and we're going to look at some real data now, because I think that's going to help get all of this, all of these things that we've been discussing solidified a little bit better. So I'll be right back. And we're back with a little bit of an R tutorial for the last 20 minutes of the class. What we're going to do is we're going to look at this prescription data. That is, first, let's load in the package into R, which is the, once again, my arrow keys decide they don't really want to work. Peculiar. We're going to load in the TSA package, which is time series analysis. It comes from a textbook. We're also going to load in a couple other packages. I forget if I'm actually going to explicitly use them, but just so that they're ready to go, we have T-series, and we have the package forecast, which are all different time series packages in R. There's actually a ton of time series packages in R, especially for using more sophisticated and different methods. But these are some of the standard ones that will have more general methods that we'll be using in this course. Right, so we have all of that. And then what I want to do is look at the prescript or prescription data. And what this is going to be, let's plot it to actually see what it looks like. Script. So this is going to look something like, well, that. And what we have here is we have the monthly average prescription drug prices in the US from 1986 all the way up to, I think, 1993 or maybe 92. I can double check that. And roughly, yeah, it's increasing. So, yep, drugs are getting more expensive. And I know the US is not necessarily known for being great when it comes to things like prescription drug costs. Hence why they all want to come up here to Canada to buy their medicine. Anyway, right, so if we use the time command, that is just type time and then put our data set into that, it extracts the time that is for our time series. So notice that the actual time starts, maybe it does start in 1987. I thought it started in 1986. I'll have to double check that because, well, anyway, the idea here is that it, the time is indexed by the year and then split into 12 increments, one for every month. But the time series data object is a little more sophisticated. So you can actually see that it has the months up here. There it is. Sorry, I was looking at the top row, which doesn't exist here, but it does down here. So it starts around August of 1986 is when the data starts and progresses forward from there all the way up to what looks like March of 1992. So sometimes looking at these for the first time can be a little bit confusing. So it's worth just exploring what a time series object in R looks like. Right, so what do we actually want to do with this? Well, again, if we want to estimate things like the AutoCovariance or the autocorrelation, the first thing we want to look at is, the first thing we want to look at is just look at the plot. And what do we see? Well, we see that it's increasing. So it's definitely not stationary in the mean. Whether or not it's stationary in the AutoCovariance is not clear, but at least in the mean, it definitely does not look stationary at all. So it's very common in time series that we'd want to try to find a trend that is occurring in our data. And we can use linear models like we would in linear regression class to do that. There are other methods that we will look into later, things like using the difference operator. But for now, let's just consider a linear model. So what I'll call model 1 is going to be what? It's going to be prescript, which is the output, and we're going to make that a function of time with prescript. So again, when I use the time command, it extracts the time variable from the prescription data set, so we have something to regress on. And if we just look at a summary of our model, what we find is that, well, okay, yeah, it's a little bit cut off here because of my margin, but the time variable or predictor or independent variable, I guess in this case, is very significant, and we get a value of 2.8, meaning that every month the price of drugs on average seems to increase by about $2.8. Now, I think I'm not sure if this is on average or per household or what. If we actually investigate the data set, our description is actually pretty sparse. It basically just says monthly US average prescription costs for the month of, and then it gives the data range. But presumably more information can be found if we actually look up this book on data analysis using regression models. But we're not going to do that for now. We're going to go back to the plot. Because what I want to do is I want to look at the, I think we can just use AB line actually, because it's a line, a simple linear regression. To plot, we'll plot this in red, the line that we just fit to our data. And we'll say line type is 2, so we get dotted. Nope, it's not doing that. Because I called it MD1. That's right. There we are. So there we have our increasing trend in drug prices. Now what we can do, there's a couple things we can do. We can look at the autocorrelation function for the prescription data. But again, it's not stationary. So while we can look at it, it doesn't really make a lot of sense to consider it. And it's always good to know that you can calculate these things in R. Whether or not they make sense is a whole other issue. So it's something we have to certainly consider. Again, the lag goes out to 15 months. We could do, say, 24 to have 2 years. And you see this steady decrease. But again, because it has a non-stationary mean, we have to be a little bit more careful. But after removing the trend, that is, if we take this prescription data and we subtract the prediction of our model 1, actually, let's not do an ACF, let's plot that. I think it should plot as a time series object. Let's see if it does. Yes, good. So now we have removed the linear trend, and if I plot a horizontal line to show you where the where 0 is a little bit more visibly, now it's okay, not quite stationary. Well, it's hard to say, right? There's definitely some periodicity. The mean does seem to fluctuate a little bit still. Now, there is a test for stationarity that we can consider, and that's called the augmented Dickey-Fuller test. It's something that we'll talk about later in this course. We haven't gotten there yet, and we need a little bit more sophistication in our knowledge of time series before we get there. But the ADF test, which is in the T-series package, is this augmented Dickey-Fuller test. And okay, it's going to say something about X having a unit root. We're going to talk about that later. It's beyond what we've done so far in the course. But the key thing to note is that by default, it tests whether or not a series is stationary, or more precisely, the alternative hypothesis is stationary. So if we have a very small p-value, that implies that our series looks stationary. And there's one other issue. that can be a little confusing when you first use a function like this is that it's stationary after a linear trend is used. So you could actually apply this to the original prescription data, and it would effectively take out that linear trend that I did manually. So just so you're aware of what happens. So anyway, yeah, let's try this thing out. But first, I want to give you some examples. So if we take, let's say, 100 normal 0, 1 random variables, this is our Gaussian white noise. It's completely stationary, uncorrelated, independent, all that stuff. So if I plug that into this test function, well, what it does is it gives me a lower, an upper bound on a p-value of 0.01. Which is saying we should reject the non-stationary hypothesis in favor of our time series being stationary. And then it even gives a warning method saying this p-value actually might be even smaller than 0.01, just so you know. On the other hand, though, if I were to take this and I were to run a cumulative summation, a cum sum, on this, then, well, what happens if I add a bunch of normal random variables one after the next? I'm getting a random walk. So this is now a random walk process. And if I do that, I get an extremely large p-value, and I'm not able to reject the non-stationary hypothesis. So these are the two kind of simple extreme cases. We have Gaussian white noise, which is very much stationary, and we have the Gaussian random walk, which is very much non-stationary, as like two canonical examples. So this is what you would expect if you ran this function. Now, if I were to actually apply this to my residuals, which, well, I guess I can do that two ways. I can use the command I did above, or I can just use the residuals command to do it manually. And sure enough, I get a pretty small p-value. So if we go back to this plot, it's telling me that while it definitely looks like it doesn't look like white noise by any means. There's definitely periodicity to it, and some other stuff going on. There does seem to be evidence that this is, in fact, a stationary stochastic process, at least based on this one test. Now, we can actually go further. If you happen to be reading my lecture notes, you'll see that I fit a much more complicated regression model because there is a periodicity in here. And if you look closely and stare at it long enough, you'll notice that it actually happens to be every 12 months or 1 year. So there's an annual cycle to this data, and we can actually toss in some trigonometric functions into our regression model to take out that trend. Now, alternatively, we can use seasonal time series models to determine this without having to stare at the data and count how far between the peaks. So there's a lot more tools we have to use on this data. But again, this is just the beginning of the course. So we're just going to use some regression methods to see what happens. So if I go back to the model that I was fitting, and we're going to call this model 2 now. Well, what I can do is actually, I forgot one thing I wanted to do. We just identified that we have a stationary series. And if we have a stationary series, then we should look at the autocorrelation function, because that was sort of the whole point of this lecture. I took a bit of a break between the written and the R coding part. So I have to remember what we were actually doing. The magic of video, it doesn't seem like any time has passed. But I actually went and got some dinner and came back. And more tea, of course, more tea. Anyway, where was I? Yes, so if we take the residual process for model 1, that is, we remove that linear trend from the prescription data. Now, according to at least the augmented Dickey-Fuller test, we have a process that appears to be stationary. In that case, we can look at the ACF, and yeah, we actually see this interesting periodic pattern. I can make that a little bit further. Let's say lag max is 24 months or 2 years. And yeah, you can actually kind of see here that you have this cycle that seems to hit another peak at 12, drop down and hit another maybe smaller peak at 24. Now, once you get out here, you're kind of below the blue line to the noise floor. But it's still worth kind of noting this pattern. And this is very strongly hinting that we have some seasonality. And as I was kind of saying before, I forgot to plot the ACF function. There are methods that we can use to model seasonality in time series. That's going to come later in the course. For now, what I was going to say is that we can go back and fit another time series model. But in this case, we can actually include some trig functions. So what I can do is I can take time and I can add, let's say, the cosine of time, but I'm going to multiply by 2 pi. And the reason I'm doing that is so that the cycle, or the cycle length of the sinusoid, will be exactly 1 year. And again, this is because I know that the cycle is a year, so I'm specifically plugging in a cosine function that has that cycle length. Other ways you can try to estimate the cycle length directly from the data without just staring at it. I think it was cosine I wanted and not sine. I put them both in, I think, in my notes. But yeah, the sine function was was not overly significant, but the cosine was. So if we look at the summary again, now we have 2 deterministic predictors that we're using. We have our time here, which, what happened to my, oh, there's the p-value on the next line. So, okay, the p-values here are still very significant. And we get 2 things. We get our time, which has now actually changed to 64. So the slope has changed quite a bit. And now we have this cosine piece, which is going to be affecting our time series. So yeah, we still got, I guess we have as much time as we want, because I can just keep talking and no one's going to kick me out of the classroom. Last year I got kicked out of the classroom a lot. So yeah, sometimes I just keep going. Anyway, yeah, we have our original plot, and what we can plot is we can plot the predicted values of model 2. And I want to say lines of the predicted value, but I have to do a little bit of R hacking and tell it that I want the time, the correct time here, as my x-axis, and the y-axis will be the predicted values by model 2, which is linear plus cosine. What are we doing here? We need a new color, red, and a new line, a bigger line, and a dashed line to make it look a little bit nicer. And it got mad at me. What did I do wrong? The lengths differ. Oh, that's peculiar. I feel like the length should be exactly the same, but let's see if we can debug this in real time. I mean, the prediction looks about what you'd expect. It's 68 long. Meanwhile, the time, the time of my prescription data is also 68. Okay, so then the question is, why is it getting mad at me? X and Y lengths differ. Did I make a mistake? Let's just get rid of all this extra stuff. Yeah, that is, oh, you know why? It's because I typed in precip and not prescript, because there's a precipitation data set in R, and that is messing me up. There we go. Let's get back our little plot features to make the plot look a little bit nicer, even if I'm running off the bottom of the screen here. So we want that. We want our line width to be a little bit bigger, and we want to use a dashed line. And now we have a new trend in our data. It's kind of neat. It does seem to actually follow, if you notice, follow the line fairly well. Maybe at the beginning it's a little bit underreporting, but throughout we do get that nice annual periodicity in the data. if we again look at the residual process, let's look at residuals for model 2, and let's use that augmented Dickey-Fuller test just to see what it says. Presumably it should still look stationary. Oh, it's interesting. Actually, it does not look stationary. Maybe it's because of the peculiarities at the beginning. That's actually quite neat, I think. That might take a little bit more thought than I anticipated. I don't want ACF. What I want to do is I want to actually plot this thing and see what it looks like. That's why. I see. See, this is what can happen when you're playing around with time series. Let's view this as a line. So what's happening here is that at the beginning, it's very much, both at the beginning and a little bit at the end, it's very much missing the mean. That is, or the mean. I'm sorry. It's under. Which way are we going here? Yeah, it's under reporting, which means that here it definitely doesn't look like a stationary mean because we start up high, we go down low, then we go up high again. So the beginning and the end definitely don't look stationary, but I'm going to take a guess and say that if I were to only take observations 12 through, let's say 60, like this, that we would get something that might look more stationary. So let's try and run the same test on that, 12 to 60. Okay, we still don't reject the hypothesis, so it still isn't happy with that. Right, so that's actually quite interesting. So what are we getting out of all this? Well, what we're getting is that time series are quite complicated, and there's many different ways that we can use to analyze them. Typically, we can use tools like regression analysis to try to extract a trend. Ideally, what we will do is extract some type of deterministic trend, like I did actually better before I tried putting the cosine in. I think things actually went a lot better. So let's go back to that to use for the instructional purposes, because when I took that linear trend out of the data, now I just can look at the residuals. And as I wrote in my lecture notes before I switched over to R, we can think of a time series, this type of time series, as maybe being a deterministic piece, like I guess a straight line that increases in time, and a stationary process. And that's what we found when I removed the straight line. See, I was trying to be too sophisticated with the sinusoids. When I remove the straight line, I get something that looks like this for my residual process. And at least as far as R is concerned, it's stationary enough, which means we can then go further. We can look at this residual process and we can try to understand, okay, now that it's stationary, what type of a time series process is it? Like I said, there's a seasonality component. There could be an autoregressive piece. And there's lots of other things we can do to try to understand the noise, the time series noise process that's underlying this prescription drug time series. Right, so hopefully that gives you a little idea of some of the things we can do in time series in R. We'll be doing a lot more later, trying to fit ARIMA models and seasonal models. And I'll actually at some point explain what this test is doing once we understand what it's talking about when it says unit roots, because that's going to be a really key part of understanding ARMA models once we get there in a few weeks. Until then, thanks so much again for listening, and we'll pick up again in the next lecture with, I believe, oh, that's right, smoothing. We have a little bonus lecture in here before we get into, that's a fun one. Before we get into the ARIMA models for time series, we're going to do some smoothing, which is actually quite a nice tools to be aware of. So that'll be another mix of me writing some notes and doing some R coding. And I'll see you in that lecture.